Basic principles that we'll look at is that for both frequency and time domain electromagnetics, you have a receiver and a source. Very similar to magnetotellurics. In the transmitter coil, a current is inputted into the transmitter coil and induces a secondary magnetic field. That's called your primary field. Okay, so if you look at let's see here. So if you look at the transmitter, this dark green line is your primary field. And if there's any sort of conductor or conductive body, it'll obviously induce secondary magnetic field, not magnetic, electrical field. And then as that moves, we have the secondary field, which is our secondary magnetic field, and that's what we measure at the receiver. The issue is this secondary field is very small compared to the actual primary field. So the difference in frequency domain and time domain EM, frequency domain EM, which is the HLEM, that's what they do is they take the primary field phase and they, through a wire, they connect it to the receiver so that we know the phase of the primary field. And then it basically takes the primary field and subtracts it so you can see the very weak secondary field. That field is very small, so this is why we moved away mostly from frequency domain EM, is because with time domain, they switch the primary field off. And then they measure, as that ring moves down, they measure the secondary field, so there's no primary field to worry about. But HLEM maximums are still used quite widely. But the big thing that we have to remember is that the secondary field is really small compared to the primary field. Okay. Again, the main targets will be conductors, same as magnetotellurics. You need something conductive to produce that secondary field. Resistors won't, and you'll get a small secondary and primary field. So when we look at the curves, you can have a look at them. Again, the basic mathematics. Ampere's law and Faraday's law, it's just the inductive fields again. The magnetic field will induce a current, the current will induce a magnetic field. But the important ones at the bottom here, this is what I added, this is how they calculate the apparent conductivity from the EM system. So it's basically a ratio between your primary and secondary magnetic field. And then it will give you your apparent conductivity. For I think it's conductive bodies, I need to double check, but either if it's very conductive or very resistive, this is true. But if it's either conductive or resistive, you need to model this out because you have signal leakage. So you'll have in the primary and secondary field, it's like with the MT, the phases will mix. So, but this is the basic principle. So, and the problem is that the secondary field is usually very small. So what we're trying to measure is on a scale, like on orders of magnitude smaller than the primary field. Main uses is obviously conductive ore bodies, groundwater, fracture fault zones, archaeology, and precision agriculture. Does anybody 31? From the transmitter and receiver is just mounted in those poles, and you have a limited length for the EM31, but it's very shallow. I mean, if you look at its frequency, it's quite high, 9.8 kilohertz. So the deepest it will explore is around 6 meters, 6 to 10 meters, depending on the conductivity of the overburden. So that's more like if you want to do archaeology stuff. EM34 is the other system we use. It's again a frequency domain system, but this one we can actually have the coil separation and different frequencies for it. So obviously the larger the coil separation, the deeper you are sounding, as well as the lower frequency. If you guys remember from the skin depth formula, the same thing applies to EM, that exact same formula, okay? So again, frequency and conductivity will play a role. And then just maximum coupling, when you want maximum coupling, you see how the magnetic fields, the direction of them. So if you want maximum coupling, the horizontal loops, if they're both horizontal, it's the maximum coupling because the magnetic fields will be moving through the center of the loops and then induce the currents in it. If you start doing vertical loops, that's minimum coupling. And so to give you different dimensionality information, but if you want the maximum signal, you do horizontal loops. Okay, it's just the way, if you can look how the magnetic field operates, and the way you're going to be measuring it. That's our system, which is the HLEM. So it has both horizontal and vertical dipoles, but we'll be using the horizontal mode. It has a range of 110 to 1400 hertz. And this is important, this is what I'm trying to figure out, is it measures the in phase and the quadrature, we'll speak about that now, in the percentage of the primary field, okay? So different systems measure these values differently, so that's what I was trying to figure out. So it seems like for the HLE, it's a percentage of the primary field, okay? That's how we connect the two, the receiver and the transmitter, so then we get the measurement. So the depth, so a rough estimate is about 1.5 times the coil separation for horizontal features, and then vertical features about 0.75. That's just how the magnetic field gets affected by these bodies, okay? But roughly, let's just go with, I think let's go conservative and just say 0.75 when they're doing their planning for the depth planning. Because it also involves the frequency, it's not just your separation, okay? But thumb suck, 0.75, their coil spacing. So yeah, those are the main frequency systems. I'm not going to go over the time domain stuff, just because depth is, as you guys can see, it's the same as magnetotellurics. So your conductivity and your frequency plays a big role in this. So when you're taking measurements with the system, make sure you know what frequency you're taking it on. Sources of noise. So spherics, which is our signal in MT, is a noise in EM because it's now producing a source that we don't know where it's coming from, and we need to know it for EM. And then cultural stuff is again electrical power line, communication equipment, so it's the frequency stuff. Nearby buildings, pipes, and landfills. And then I want to add again is any agricultural equipment that's got to do with irrigation. It leaks a lot of current into the ground. Power lines proportional to coil spacing. So you have to look at your skin depth again and the spacing. You can calculate how far you need to be away from a power line so that it won't affect your source. But as long as you're going parallel to a power line, you should be okay. Don't run perpendicular to them, because you're going to start getting interference because how the magnetic fields operate around a power line. Okay, so that's just some noise sources.